We're very happy to have our first speaker of today's session, Nicklas Ramberg from Mainz, and he will talk about bubbles from Dark Confinement with holography. Please, Nicklas.
All right. Thanks a lot for the introduction. And yeah, as mentioned, I'm going to talk about something titled as Bubbles from Dark Confinement with Holography. And this is work I've been working through with my PhD advisor Pedro Schwaller and Enrico Morgante here at Mainz. And to set the stage, I would just like to first off provide with a brief outline of what I'm intending to talk about. So first off, say a few words of why we intend to look at Young-Mills theories. And the phenomenology mainly concerning this work is going to be in regards to trying to see for aspects of gravitational waves. So I would like to say a few words about how to think of gravitational waves generated from first order phase transitions. Also understanding the confinement phase transition with holography. We're going to be talking about a model that's called improved holographic QCD, how one thinks of this at finite temperature, and in regards to Hawking page phase transition, and in regards to also incorporating features of SUN lattice thermodynamics, how we intend to develop an effective potential, and also being able to postulate an effective action to conduct thermal tunneling, have a look into the predict gravitational waves from this. And yeah, that's my intended outline for the talk. So, okay, first off, a few words about SU and Young-Mills theories. Essentially, in the standard model, we almost have them, not exactly in the notion of regular QCD. However, they are a very minimal extension to the standard model, and they can actually, by themselves, actually stem in various applications. So, for instance, in what is dubbed as TH for twin Higgs models as potential solutions to the electric hierarchy problem, where SUN Young-Mills theories stem as the low energy content of such a solution. Potentially also in the notion of having composite dark matter candidates, either by glue balls or weak baryons, depending on if you look at these theories for with or without flavor. However, part of the motivation of the phenomenology of this works stems in the context of string theory, since in string theory realizations, it's fairly common that you have many residual gauge sectors, and in many cases, they tend to behave as pure Young-Mills theories. Nevertheless, these theories are strongly coupled. So to be able to have a proper tool in regards to treat with strong coupling, we intend to utilize the ADS CFT correspondence in trying to see what we could say about the first order phase transitions, and hope that the utilization of ADS CFT could help us say something about gravitational waves as well. And furthermore, before we go into how to think about gravitational waves from first order phase transitions, an important point to bear in mind is that we do actually have first order phase transitions already in nature. For instance, in water, superfluidity, or solids at high temperature or pressure. So the leap here would be to start thinking about how to think of this in the context of the early universe. So the scenario I would like you to bear in mind is that you have a particle associated with the minima at a very high point of very high temperature, and as the temperature of the universe decreases due to the expansion, a new minimum develops, and the particle would then like to rest in a state of which actually relies to the true minimum, such that it would either proceed through by tunneling the associated barrier in between in regards to fluctuations. Nevertheless, for such a process, what actually happens when this actually takes place in the early universe is that you start to nucleate bubbles of true vacuum within the universe that is filled with the false vacuum denoted as blue, and with these bubbles associated at, let's say, these slight contours of them. What these bubbles then tend to do is that they further on expand and eventually collide. These collisions and the fact that the collisions also cause a great amount of extent of long-lasting fluid motion, which causes sound waves. And these are direct sources of gravitational waves due to the fact that it generates anisotropic stress in the energy momentum tensor. So, given the fact that in the early universe, so far as what we know in regards to the phase transition we possess in the standard model, either in regards to electroweak or QCD, neither of those are first order. So if there were to be a remnant relic or an observable that a first order phase transition took place in the early universe, for instance, by detecting a gravitational wave, could be a way, would be a direct sign of beyond standard model physics. So even though, this process furthermore also continues along until you have filled the full true vacuum with the new phase. To bear in mind that this phenomena is highly non-trivial, out of thermal equilibrium and such. The gravitational waves emitted from such a phenomena can actually be fairly well characterized by understanding only a few can be characterized in understanding a few parameters. For instance, what is dubbed as alpha here, which more or less regulates the overall height of the spectrum, since here we have a kind of a mock gravitational wave spectrum from a sound wave source, which is what we're going to be focusing on in this work. And alpha describes the amount of energy release, aka the amount of latent heat that is released throughout the phase transition. What is dubbed as beta here denotes the bubble nucleation rate, aka the amount and size of bubbles we nucleate within a Hubble volume. Also characterized in the notion of understanding how fast these walls actually expand and eventually collide in each other, and the temperature of which the gravitational waves are emitted, which is at the very end of the phase transition. Sorry for that. And just to provide, let's say, with a brief outline of the pipeline of the work, is that, okay, in this context, we're working with strongly coupled QFTs to try to work out how we could say something about the relevant parameters for gravitational waves emitted from first order phase transitions, especially in strongly coupled QFTs. There are not very many available tools. So an intended ambition here was to try to use the ADS CFT correspondence. Furthermore, by using the templates provided by the LISA cosmology working group, such that we can obtain SNR curves to actually compare with actual experiments. So I guess that's starting off setting the stage. And then let's say the last part of introduction to this will be the fact of also introducing the last key element that we're intending to use, which is the ADS CFT correspondence, by starting off with string theoretical correspondence by considering the objects as d-branes in the associated various limits. For instance, you start with a stack of d-branes at weak coupling. And look at the associated low energy theory of that. You end up realizing that you would have conformal field theories. However, if you start to realize, or let's say spend time looking at the associated other limit of strong coupling instead, you would find that you would form an object associated as a black brane, which is more or less like an extended black hole, more or less. And then by looking at the near horizon limit geometry, aka the associated low energy in this context, you would realize that you work with a string theory in anti-series series space. And the correspondence then states that there should be a correspondence between these two theories by the low energy CFT living on the boundary, meanwhile having the interior of being the associated string theory in ADS in d+1 dimensions. And one can see this, let's say, in a very agnostic illustration of the following, that you would have your gravity theory living in the interior, and then you have your CFT being associated boundary. A few features to bear in mind that is going to be useful for the talk. Since there's a correspondence between the theories, you should also implies that you would set equal the partition functions theories. This also implies fairly directly that you have a correspondence between the generating functional of the CFT with the on-shell action on the gravity side. How to think of the associated temperature of the CFT or field theory would be the associated of the Hawking temperature in the ADS notion, in the sense that one was initially working with this type of black brane object. particularly in the similar sense for the entropy by using the area law. And an interesting limit, which is going to be served as fairly important here, is when you actually go into a large n case, is that you get to the, let's say, the classical limit of the string theory, which stems you with GR in ADS D+1 dimensions. Since we're intending to employ bottom-up holography, this is an important limit to bear in mind of. So the model of interest that we're considering here is, since we're employing bottom-up holography, we're kind of doing the opposite way around, which in this sense means that you more or less assume that there is a correspondence. And then, so okay, in this case, you do not necessarily know which string theory, for instance, would have this associated low energy gravitational theory, for instance, for describing the pure Young-Mills. But in the sense of assuming that there is a correspondence between a Einstein dilaton gravity in ADS5 to 4D large N Young-Mills. And this model of improved holographic QCD was developed by Elias Kritsis, Francesco Nitti, and Ugo Gerso in around 2007 or so, to a fairly large extent. It's associated, let's say, by starting off with the action, contains an Einstein-Hilbert term and a Gibbons Hawking term for the boundary. The matter content is fairly easy in this case, having an associated kinetic term for the extra scalar, the dilaton, and the associated dilaton potential. However, since we do know a lot of the features of Young-Mills theories, for instance, asymptotic freedom in the UV, how confinement happens, area law of the Wilson loop, associated linear global spectra and such, a lot of these things end up being incorporated in the features of this associated dilaton potential. And the dilaton in this context is realized as being dual to the associated running of the Toft coupling on the gauge theory side. And by studying the associated action in either in a black hole context or a thermal ADS, is going to be describing the different phases of our Young-Mills theory in the notion of a Hawking page phase transition. So a few features about the potential and what features we actually need to be able to reconcile with what we know of Young-Mills. So first of all, we won't be able to reconcile asymptotic freedom in the UV in regards of the associated running of the beta function, which in this case implies for the potential that you should go as a continuation of a power series. And in the aspect of the IR would be that it shall, since okay, there we would have notion of confinement, we would have the aspect of the linear global spectrum, and also the fact that we would have an area law for the Wilson loop. We obtain one show through quite a bit of work that the potential should possess the following asymptotics in the IR. And what notion of UV and IR here is that lambda, aka the dilaton for small field values, corresponds to the UV, and for lambda going to, let's say, infinity / very large values, corresponds to deep in the IR. And a assumption that respects these asymptotics is the following one in the bottom. And what we do in regards to being able to incorporate features of SUN lattice thermodynamics is to fit the free parameters to available lattice data, which are the dots, and which are fits corresponds as the full lines. And we then use this, let's say, as the initial point of when we want to study the associated phase transition that this theory possesses. However, we're also further on keeping on going to the fact that we want to elaborate this on finite temperature. And finite temperature in these aspects, in these pictures, what you then end up looking into is the fact that your high temperature phase ends up being described with a black hole, with an ADS Schwarzschild black hole, for the deconfined phase of the Young-Mills theory. And the low temperature phase, aka the confined phase, is being described with a thermal ADS. And what notion of a thermal ADS here would be that you would do in finite T QFT by introducing imaginary time formalism with a periodicity of the time component. So how this more or less, let's say through this illustration kind of looks is that you are at a high temperature, you describe the physics notion of the black hole, and you could show that black hole or the thermal gases, the respective ones, phases for higher or lower temperature by looking at the dominant contribution in the partition function, for instance, in the high temperature case. And you can also see it, let's say, heuristically by the appropriate scalings in regards to the number of degrees of freedom by the black hole or thermal ADS in correspondence to the number of degrees of freedom in the gauge theory. That's another way of thinking about it. You start off decreasing temperature and end up having an intermediate phase. And that once you decrease temperature low enough, aka when the black hole solution ceases to exist, you're predominantly in the thermal gas phase. Furthermore, a few notes to take into account is the fact that we do indeed consider regular black hole solutions, aka that the Hawking temperature should equal the temperature of this, that the Hawking temperature of the horizon should equal the temperature of the surrounding thermal ADS gas surrounding the black hole. And for the area law, for the entropy, we consider the area law, and for the free energy, we work out the difference between the actions of the ADS black hole and the thermal gas, and by working in this kind of the subtraction between the two also serves as a way of regularizing the actions, because these actions tend to suffer from UV divergences. And this should also be thought of as free energy density, since we're dividing out the free space volume. And beta is 1 over temperature from the notion of periodicity of the time component. So to bear in mind of a little bit of thermodynamics, I should have mentioned this. Given the fact that the blackening factor that you take into account for Hawking temperature possesses an absolute value, could already tell that that you would actually have multi-valuedness for the profile of the temperature. The graphs here should be understood that lambda h is actually the field value of the dilaton at a position of RH, where RH would be the position of the horizon in the 5th dimension. And you have the associated branches of left and right. You have the big on the left side, because deep in the UV you could show that you have a 1 over the radius, which provides with how you end up with a big black hole towards the left side of this, and the small black hole branch to the right. And by taking into account where you have this lambda h min here in the bottom, which is actually the temperature which below that the black hole solution ceases to exist, and you're only for temperatures lower, you're only stuck with the thermal gas solution, and that in the aforementioned illustration could be thought of this T0 temperature here, for instance. And to bear in mind of this for the free energy curve, you end up following, let's say, the big black hole trajectory, follow along the associated branch. At some point, start following the small black hole branch. However, you cannot follow the small black hole branch for too long, since they are thermodynamically unstable. So what we're going to be doing here is going to effectively use the small black hole branch as an instanton to interpolate between the big black hole to the thermal gas. And by doing so, by doing this, we would also need to bear in mind of the relevant order parameter, to be able to conduct and study a phase transition. And the relevant order parameter here is the dilaton field value at the horizon, dubbed as lambda h, aka lambda of like the dilaton field value of the radius valued at the horizon rh. And the intended approach, and okay, in conventional senses for the order parameter, you would think of having, let's say when you look at this in 4D young males or so, you would look at the thermal version of the Wilson loop, or let's say the vacuum expectation value of the Polyakov loop, and see that it has that it jumps discontinuously. However, given that we intend to employ the free energy landscape approach, so I would like to briefly mention how this works. So what we do here is that you to be able to so what we do is that you select a certain direction in field space which interpolates between the big black hole and the small black hole. Since here we're intended to use the small black hole as a for a brief period as an instanton. So what we want to do in this approach is to choose a direction in field space as we interpolate between the big black hole and the small black hole by assuming specific ansatses for the metric and field configurations. And what this effectively does is that it reduces the field space directions to only one field. So in the context of numerics and potentially complicated scenarios, this kind of simplifies things quite a bit. However, how we do this in practice is that you construct field and metric configurations for the associated solutions to the Einstein equations. However, you do realize one thing when you do this is that you end up violating the regularity condition of the black hole, aka that the temperature of the system, that the temperature of the surrounding thermal gas is no longer necessarily equal the temperature of the black hole. And what happens when you do this is that you develop a conical singularity. And when you have this conical singularity, what you have to do, well, you have to remove it by regularize the contribution this would generate to the action. And how to do so? You regularize it by imposing a spherical cap and push up towards the end of the tip of the scope to regularize the tip of the cone. And by calculating this, by calculating this and adding this to the free energy we had initially is how we describe the effective potential in this context. So what
Sorry, Nicklas, just to remind you, you have about 3-4 minutes left.
Yep. So the few points that I'd like to bring to attention is that in the case when we do not have the conical singularity, aka for regular solutions, we have a black dashed line. And by utilizing this approach to construct an effective potential, what we obtain is that we obtain a branch which considers the minimum, which describes the big black hole branches, and a maximum, which describes the small black hole branch, and an additional minima once you take lambda h very far to the right, which corresponds to the point where you would have the thermal gas. And by seeing that you have an intersection, provides that you actually have that stationary points of the effective potential corresponds to regular solutions to the Einstein field equations, because at those points you recover the fact that you have that you have regular solutions on those points. And we can show the associated formula that we obtained for the effective potential. Okay, now we haven't explicitly shown how the free energy looks initially. And by having this part essentially by working out in this fashion, we choose the following normalization for the kinetic term with a free parameter c, which is something we are ongoingly working out exactly what it should be for having a framework of constructing these effective actions in a more generic sense, and show how this depends for the gravitational wave spectrum in the end. So the nucleation, or more or less the tunneling here, proceeds by the fact that you have nucleation of a bubble which interpolates between the big black hole solution at infinity and a singular configuration in the center, which rapidly decays to the ADS thermal gas phase due to the fact that the small black hole is thermodynamically unstable, and one can show by working out the fact that the duration of the phase transition is so fast that you never really have a chance of wander away in the small black hole branch. And to more or less finalize these comments, we formulate this associated effective action for thermal tunneling, described by the expression here for gamma. What you then do is that you compare the thermal nucleation rate to the Hubble expansion. And when this is of order 1, this is where you would effectively nucleate one bubble per Hubble volume. And the temperature of real relevance is the percolation temperature, which is the temperature when the probability of a random point either being at a false or a true vacuum being of the same magnitude, aka that you've filled, let's say, half of the universe with the true vacuum in a universe that's initially filled with the false vacuum. And by working this out, we obtain the following, let's say, insights for the parameter of values. But let me show it more in this sense, which I think is the more proper way of showing it. And this is going to be the last thing I want to show. So the bands here corresponds to the error we obtained by actually having a free parameter in our kinetic term, which we dubbed as the coefficient C, by varying by order of magnitude, which indeed provide with moderate dependence. We treat the wall velocity as a free parameter, and that is something we're ongoingly working out by using some other holographic techniques. Signals are fairly small, unfortunately, for this when we try to look at this for an SU3 case. But if one were to, for instance, consider working at very large N, you would suppress nucleation further. You could expect larger gravitational wave signals. But the takeaway message I want to bring with this, I think, stems more or less from my summary that start off by looking at very minimal extensions of the standard model. We try to actually resemble in this notion QCD-like theories, because we're not looking at SUSY Young Mills here, we're looking at normal Young Mills. And some of our uncertainties, the understanding of wall velocity, the normalization of the kinetic term, perfect the lattice fit, and some of our ongoing outlook. And with that, I would like to gratitude for your attention, and thanks.
Okay, thank you, Nicklas. Thank you for the interesting talk. Are there, maybe we have time for one or short question? If there's any? Yes, please, Marcus.
Yeah, so one short question. Now that you have this dark confining sector, can you try to use it also for, let's say, a dark matter abundance in glue balls and get additional data that, you know, tells you where to look or where to match?
Yes, that you can indeed do. This is actually something we are working out a bit at the moment. Is to work out in these theories by understanding how one does glue balls in the context of holography, which, okay, it has its, let's say, it has its ways of doing it. By you consider for instance, if you want scalar glue balls, you take scalar fluctuations towards your metric, you work out the fluctuation equation, and then you regain the spectrum and write it down as an effective Schrödinger equation and such. And indeed, this is something that we're looking into by, for instance, looking at larger NC where there's still lattice data, and then further on really pushing, let's say, the NC limit, in which you would also have more, let's say, certainty of the duality, given that we're doing this in a bottom-up framework where one could, of course, could ask, well, you're cutting off N, when should you start caring about, for instance, string corrections and such? And this is indeed something you have to, let's say, look out for. and pay a great attention to, I would say. But yes.
Okay, thank you very much.
Okay, let's thank Nicklas again.